mean, if I can put a finger on that, it seems, well, first, I think what Chris is describing is what you described as conventional, and maybe you had boring in mind, kind of multiverse kind of picture of what's going on that you wanted to.
No, it wasn't really boring. It's just that, the idea that
but I take it
anything about the multiverse should be conventional was funny to me.
But I take it if you tried to read what Chris and Craig were describing into the infinite causal sets that you're thinking about and sort of imagining a post somewhere, in one half, time would be running in the direction of the arrows. In the other half, you'd have to have time running in the opposite, contrary to the arrows. It's not like in the bottom that the arrows are pointing down, right? They're always sort of pointing up. So it's kind of built in that it's not like that in that sense. And I don't know if that's what you and Craig were kind of considering, that possibility. So we do have one more question from Antonia Hildebrand, please.
Yes, you said that the elements of these sets are events, and I was wondering, how are events defined exactly in this context? So which kind of things are ordered?
That's a great question, thank you. I suspect I was a little sloppy about the term event. So I should say, to be more precise, that the elements of the set are atoms of space-time, and they are, if you like, somehow the building blocks of events. They're the smallest things that can happen. I mean, what does it mean for an atom to happen? It means that the atom comes into being. So there's, if you like, something that happens. So the term event is, it has many meanings, sort of colloquial meanings and specific meanings in mathematics. And so I think I probably conflated them all a little bit in a confusing way. So apologies for that. At the very basic microscopic level of the causal set in itself, the elements of the set are space-time atoms. They're the most basic entity that space-time is comprised of. And if you like, the event, meaning the thing that happens that corresponds to that atom, is the atom coming into being or becoming. So that's one concept of event, which is something that happens. And then in the stochastic process, which is the other framework that I was talking about, this concept of event, an event, that's a sort of term that's used in the technical terminology that goes along with stochastic processes. So an event is a subset of all the possible histories of the stochastic process. So if you think about, a simple case might be a random walk is a stochastic process, or let's say a random walk on the integers, right? And an event, an example of an event is after 15 steps, the walker is within 2 steps of the of where it started, right? That's an event, and there's a bunch of trajectories for the walker that satisfy that, and there's a bunch that don't. So you put all the ones that satisfy it into a set, and that's called an event. And so that's just one example, but all together those events form an algebra of events. So that's the other way I was using this terminology of event in the talk. So maybe I wasn't clear to distinguish those things.
Okay, and what's meant by space-time atoms exactly, if I may ask that?
They are fundamental units of reality.
So you mean atoms, or is it something
I don't mean atoms as in, regular atom, atoms of matter. I mean atoms as in indivisible pieces of space-time. That's
Okay.
so atom, in its etymological sense of being indivisible. So it's the smallest and indivisible units of space-time.
Okay, thanks.
Thank you. Okay. Well, I'm going to abuse my hosting and chairing privileges, I think, to ask the last question of this series, which is actually kind of a follow-up to Siddharth's question. But let me ask the question. So this way. So there's a density of the nodes or the events of sort of one. So I understand what that means in the situation where, I understand sort of empirically, at least, what that then means in the case where the regime where the causal set is being approximated by the continuum. But how would you understand that in the sort of non-manifold, like sort of parts of the causal set? Does that make sense? I think that's kind of getting to what he was sort of asking. Yeah, okay. Another way of getting at what he's asking.
Right. I think it doesn't have a meaning. I mean, the density is. It only has meaning in the discrete continuum correspondence. So when the causal set is not manifold-like, there is no density. I mean, the only thing you can say is that it's locally finite. So in that sense, it's discrete. So there's no accumulation. There are no two causal set elements with infinitely many elements in between them. So there's the discreteness, but there's no density as such in it for parts of the causal set that are not manifold.
I think that that's kind of what I expected you to say, and I think I would say sort of think about it from that point, that this density postulate is a postulate about how to relate the underlying theory, the causal set theory, to the continuum space-time, that we experience. So it's a sort of postulate about how to reduce space-time to a causal set, and then in a case where it doesn't reduce, then it's not actually in play.
That's right. So another way to say it is that we like to say that the discreteness is Planckian. It's a Planck scale discreteness, but that has no meaning for the causal set in itself. You just have a causal set. It's a discrete thing. It doesn't have any scale. But for a causal set which has a continuum approximation, then we would say, well, we experience the causal set in this way, and in the correspondence between the approximating continuum and the causal set, then the density comes into play, and the fact that it's at Planckian scales is meaningful in that context, but not in general. I mean, not otherwise.